All right, this is assignment 4.5. There it is. Set up here. So this assignment lesson has to do with understanding the connection between the graph of a function, the graph of a derivative, the graph of the second derivative. So I think a number line is going to be helpful here. And at first, conceptually, it's a little bit challenging. If you allow yourself to practice, give yourself an opportunity to learn it, practice, give yourself a chance. I think you're going to catch on to this. So first it says sketch a graph of the derivative of the graph that's shown. So I'm gonna just sketch that here in my notes. What I obviously notice is that it is a slanted line, and that derivative means the slope. And in this case it's a line, so the slope always stays the same number. So if I take two numbers, 2 points, and count rise over run, I count up 3 and to the right 1, and so I see the slope of the line is 3. Now that is the graph of what y equals. So what would y prime equal then? So the graph of the derivative then, you would go, let me just do this. So there's a quick sketch of the slanted line. I know that derivative means slope. So the slope here is the same, it's at 3. So for a slanted line, the derivative is always a horizontal line because it never changes. It's a constant. In this case, it goes through 3. So the y and y prime. Number 2. In number 2, you have parabola. And again, we're going to take that parabola and find the slopes and then graph the slopes so you know what the derivative looks like. Now for a parabola, it's not like a slanted line, so we're going to talk about that. So when we talk about slopes here, we're talking about increasing and decreasing. So when I look, and we have endpoints at the end, so I need to be aware of that. So starting at -1 on the x, there's an endpoint there at -1 and 4. So if I follow the graph, it is decreasing. So what I'm going to do is I'm going to do a first derivative number line. And off the graph, I know when the first derivative equals 0 because it's the turning point. So that's when x equals 1. So before 1, it decreases. And then after 1, it increases. So, and if it is the graph, which it is, of 2x, I could even have a sense of that. So this graph is x squared. It's actually moved 1 to the right, so it's x minus 1 squared. I don't need that if I'm just sketching, but it could be helpful. So I recognize that this is just a parabola shifted 1 to the right. So I could expand it and take the derivative and graph it, but I want to also just focus in on this. So at +1, the derivative is 0. So right there, this is the derivative. So the derivative is 0 when x equals 1. Before 1, it's negative, and after 1, it's positive. So it's going to be a slanted line, and I want you to notice that before, and at -1, sorry, there's an endpoint, and where's the other endpoint? That 3? So on the right, yeah. So I just got to be aware of the endpoints. So we have, so ignore this point, -1, 1, 2, 3 here. So we have a line with endpoints because it doesn't go on forever. The most important part is we recognize when the derivative is 0. That is the turning point. And then positive means above the axes, negative means below. The derivative of a parabola, like x squared, the derivative is going to be a slanted line. That's also helpful to know. Number 3. Here we go. So in number 3, you have a horizontal line. So what I care about this horizontal line for number 3 is just the slope. And for a horizontal line, the slope is 0. So if I want to graph the derivative, so derivative means slope. What is the slope of this line? Well, it never changes. It's always 0. So maybe I'll do it in a different color. It's going to be a horizontal line right over 0. So that in purple there, that's the graph of the derivative. So everywhere, the slope of this line is 0. That's what the derivative shows, the slope of this graph. Number 4. This is an absolute value function. So I want to be able to graph this. So there's a quick sketch of it. See, what I'm intrigued by is here to know that at a corner the derivative is undefined. So at 0 is going to be a hole because the derivative is not defined. But to the right, this part to the right is a negative. It's decreasing, and it's decreasing at a rate of down 1 and to the right 1. So can you find negative 1? And then to the right, it's at negative 1. This shows the slope. So what is the slope to the right? What number? Down 1 and to the right 1. It shows the slope is negative 1. Notice the hole because it doesn't exist. And it doesn't exist because you have two slopes at the same time. How about the other side? Notice it's rising, and you go up 1 and to the right 1. So for this one, on the left, the slope is positive 1. So positive 1, negative 1, and it doesn't exist. So to the left, the slope is positive 1. It doesn't exist. The jump is there. And then to the right, it's negative 1. All right, next one. So for this one, you're given the graph of the derivative. So for the graph of the derivative, we're going to be working backwards to try to understand what information am I given here. So let me just scroll down here. And then I'm given a starting point. If you don't get a starting point, you can't sketch it. I mean, you could sketch the curve of it, but it could be floating up or down. Like 0, 0 gives an anchor to the sketch. If you didn't have that, the picture would be correct, but it could be up or down or whatever. This anchors the picture. So it's good to have a starting point. When I look at number 5, if that's the derivative, I'm going to do a first derivative number line just to be able to understand it a little better. So where is the derivative 0? Right on the graph, and it's 0 at 0. So at 0, it is 0. Let me just do this here. So at 0, it's 0. Before 0, it's above, and then after 0, it's below. And another thing we could look at here is we can look at the second derivative. Now, the second derivative is the derivative of the derivative. So when I look at this, if I want to know what the derivative of this is, it's just the slope of this. So this slope is down 2 and to the right 1. And it's negative throughout. So the whole slope is negative. It's decreasing. So what does that tell me? So this tells me it's concave down throughout. This tells me at 0 there's a maximum because it rises and then falls. So when I want to sketch this, since 0, 0 is an anchor point, 0 is going to be a maximum. And then the whole thing is concave down with that maximum. So it rises and then falls, and there's a sketch of what y could look like. And the important part is that this matches this. So does it increase and then decrease, and is it concave down throughout? So this matches this, so there's a good picture. Number 6. In number 6, you're given again, the graph of the derivative. Now, what am I looking for when I look at it? So I'm going to do a number line off this, both a first derivative and a second derivative. So I'm going to remind you that the first derivative gives me increasing and decreasing. So when I look off a derivative graph, I'm looking, is it below or is it above? So first of all, oh, and there's ends here. So -2 to +2 it ends. So I'll make sure my number line goes from -2 to +2. So first, from -2 to -1. So at -1, the derivative is 0 because it's an intercept. The other intercept is at +1. So on my first derivative number line, -1 and +1, because the derivative is equal to 0. That's another way of saying an intercept for the derivative. Next, I look between -2 and -1, it's below, so I put a negative. Then from -1 to +1, it's a positive. And then from +1 to +2, it's a negative. The next thing I look, is there a turning point for the derivative? And there's a turning point at 0. That's going to be the second derivative. So when I look at the first derivative, the turning point tells me when the second derivative is 0 and if we have a point of inflection. So when I look at the first derivative, the turning point is when x equals 0. And before that, it increases, and then after 0, it decreases. So I created my number lines, first derivative and second derivative. Just want you to see it off the graph. So you have to be very good at interpreting the graph and understanding what you're looking at. So for a first derivative graph, I'm looking for the x-intercepts, and then I'm looking for, is it above or below? For the second derivative off the first, I'm looking for a turning point and whether it's increasing or decreasing. That takes practice and studying to see it. Next, I need an anchor point. Sorry, I didn't know what the anchor point. 1, 2 is our anchor point. Okay. So 1, 2 is our anchor point. And so recognize here. So if it decreases and then increases, -1 is a minimum. And then it increases and decreases. So +1, which this is a maximum. So what they gave us as an anchor point is a relative maximum. And probably an absolute maximum between -2 and +2. It is one between -2 and 2. So -2 and +2. Let's start with our anchor point, which is at 1 and 2. So we can start there. That's going to be a high point. So I know that after 1, 2, it's going to decrease with a frown. In fact, it's going to frown and at 0. So I'm just going to create a point here. It's going to frown like this. So it frowns, so it's concave down, and from 0 to 1, it's increasing, and then from 1 to 2, it's decreasing. So that's good, and it's an endpoint. What's going to happen at -1? I need a point that's below. You say, where do you put it? I'm just focused about the sketch of it. So whether you put it at +1 or -1, -2, -3, I'm looking at the curve of it. So I know that it's not concave down. Now it's going to be concave up. And so what I'm looking for is, are these matching? So you have a negative, a positive, and negative. And recognize you don't have enough information to know the other points in terms of what we're looking for. So I'm just looking at negative, positive, negative. So in other words, does it decrease and then increase and then decrease? We have our turning points at -1 and +1. From -2 to +0, it's concave up, and then it's concave down. And so this matches this. That's where we need to get at. I know it's not simple, and you have to think, interpret, and be able to feel your way through it a little bit. We're going to practice again. So number 7. So for number 7, that's your derivative in this case. So again, I'm going to and we have a starting point at negative 1, 2. So I'm just trying to get the information I can off of it. So if this is your derivative, I'm going to do a number line for it and think what's important again. So let's go through that again. What are the x-intercepts of the first derivative? At negative 1 and at positive 1. Those x-intercepts is when the derivative is equal to 0. When I sketch, it's going to create a turning point. So before negative 1, it's below. Between negative 1 and positive 1, it's above. And then after positive 1, it's below again. So this tells me my function y is decreasing, increasing, decreasing. So this is a minimum, and then this is a maximum. So at negative 1, 2 then is going to be a relative minimum based on this as my anchor point. Next, I'm going to do a second derivative number line. What am I looking for there? Well, I'm looking for a turning point or where it is undefined. In this case, at 0, it's undefined. So it's either going to create an asymptote or a hole. So at a sharp corner, the derivative is undefined. So it's not just where the derivative is 0, it's also where it's undefined. Well, before that, it's increasing, and then after it, it's decreasing. So concave up, then concave down. This is not a point of inflection because it's undefined. It's not a point. It's an undefined point. And it would be, we're looking at probably a hole when we put it in there. But we're not graphing the second derivative anyways. So for this case, we're just looking at concave up and concave down. This doesn't mean that this is undefined. So when I go backwards, the point on the function is still defined. The second derivative is undefined, not y. All right, let's put this together. So I'm going to start with what I know. So negative 1 and 2, that's going to be a minimum. Now, what do I know from this? And then just work backwards here. So I know it's going to decrease, and it's concave up. So decrease, concave up. So let's just start that part of the graph. Decrease, concave up. What happens at 0? So it goes like this to 0. Is that now it's going to be concave down. But when it's concave down, it's still going to be increasing. And then we have a turning point at positive 1. So we're just building this graph. So concave up, concave down. See how our turning points are at negative 1 and positive 1 in terms of a minimum and a maximum. And then what happens after positive 1? It decreases, and it continues to decrease concave down. And does this match this? So just go one at a time. It decreases, then increases, then decreases. At negative 1 is a turning point. At positive 1 is a turning point. Concave up, concave down, and it matches. Number 8. So in number 8, we have endpoints at negative 2 and positive 2. So let me just do this. And we have an anchor point at 0, 0. All right, so I'm going to do a number line for this. So what am I looking for when I do a first derivative number line? What are the intercepts? So these actually are ends right here. Sorry. So that's at negative 2 and positive 2. So there's not going to be turning points because they're ends. So you can't have a turning point if you don't have something before it and after it. So I'm looking for this one right at 0 is our turning point. But between negative 2 and 0, it's below, and then it's above. So at 0, this one, 0, 0, that's a relative minimum because it decreases and then increases. For the second derivative, I'm looking for turning points. So we have a turning point at -1 and another one at +1. So now I'm looking at the turning points for the second derivative when I look off the first derivative. And what I'm looking for is decreasing, then increasing, and then decreasing. So when I go to my graph of y, when I sketch it, this tells me concavity, this tells me increasing and decreasing, and I put that together for y. It's being able to fit together y, y prime, and second, y double prime. The first derivative, the second derivative, and the function, and how they connect, and what information you can get off their graph when you look at it. All right, let's put it together. Start with the anchor point, which is at 0, 0. I know that's a minimum, right? 0, 0 is a minimum. So what do we know? So at -1 and at +1, let's start to the left. I need a point here above because it's decreasing, but I need that point to show concavity. So from -2 to -1, so I'm going to pick a point above this because it's decreasing, but it decreases with a frown, and then it decreases with a smile all the way to 1. So it frown, smile, and it creates that turning point. And after 1 is concave down, but it increases up to 2. So at the end, you see, does it match? So first of all, decrease, increase, that's fine. Here, concave down, concave up, and then concave down. So both the concavity and increasing and decreasing match, and you use your anchor point. All right, number 9. So use the graph of the derivative shown to sketch a graph of the second derivative and a possible graph of f. So what you're given there is a graph of the derivative. So off that graph, let's come back here. So here's the graph of the derivative. I'm just going to call that f prime. So if I did a number line, I want to know where either there's a turning point or where it's undefined. So you can see it's undefined at 0. To the right of 0, it's increasing. And then to the left of 0, it's neither increasing or decreasing. It's just a constant. And so that means to the left, that answer, the slope is 0. So I'm just going to put a 0 there. What means that I need to draw a horizontal line that's 0. So this one is neither increasing or decreasing. That means the slope is 0, so I need to show that. If I do the second derivative, oh wait, just hold on a second here. I've been doing it, so let me back up. Off the first derivative, are there any x-intercepts? So there's no critical numbers, but at 0, sorry, I still have 0 there, it's undefined. So are the x-intercepts? None, but where is it undefined? It's there. And what I look at, is it above or below? So for both sides, it is above. And that's a line. This line here is just y equals 2. So if I did the antiderivative of that, it would be 2x if I was working backwards. Because 2x, when you take the derivative, gives you 2 in terms of what direction you're going. Here, at 0, again, when it's undefined, now we look at that, where on the left, the slope is 0, and on the right, it is increasing. But it's increasing constantly at 1. So constant going up at +1, this one at 0. So let's see if we can put the pieces together. So the second derivative should be super simple. So the second derivative is here. So up to 0 here on the left is the answer. So the slope is 0, so I just show 0 on my graph up to 0. Put a hole there. And then what happens to the right of 0? Now the slope is 1, so then you just show a horizontal line at 1. And what this shows is what the slope is over here. So when it's to the left of 0, the slope is always 0. When it's to the right of 0, the slope is always 1. This shows me the slopes and what their values are. How about the other way? How about the function? What is it going to look like? Do I have an anchor point for that? I don't know if I didn't even see. No. So I can just sketch it. I can create my own anchor point. So when I look at this one, obviously something important is happening at 0. There could be a hole here or it could be a point. But the important part is that to the left is going to be a slanted line, and it's a positive slanted line. So to the left is going to be this, and the slope of this line is 2. So up 2 and to the right 1, that's what this is. So this is the actual function. It has a slope of 2. That's what I saw here. And then to the right, what is this? If I work backwards, well, it's increasing. And if this is up 1 over 1, like if this is y equals x, then the antiderivative, right, would have to be 1/2 x squared, because when you take the derivative, it's equal to that. But in other words, it's like a parabola that folds up. Recognize the right is concave up, and then on the left, there is no concavity. So, and there could be a hole here or a point here, and does it match? So first of all, is it increasing throughout? Is the concavity match? Does the slope match? In putting all the pieces together, right? Not simple to think conceptually. Number 10. So in number 10, I'm just going to do a number line and then go from that. So the first derivative number line, the x-intercepts are at -6, are at 0, and at +6. So this one starts below, then after -6 it's above, it stays above, and then after 6 it goes below. So that's going to tell me increasing and decreasing. So let me show you what mine looks like here. So I just took the x-intercepts and went, it's below, it's above, it's above, it's below. And because there's no sign change here, there's no turning point. Only when there's a sign change. So at -6 is a minimum, because it goes negative and then positive. At +6 is a maximum, because it goes above and then below. Just following increasing and decreasing. And at 0 is neither. Now, on the second derivative, I put the turning points. So at what x values do we have a turning point? So at -4, we have a turning point, at 0, and at +4. And now I'm looking at increasing and decreasing. So this starts increasing, then decreasing, then increasing, then decreasing. So let's go back here. Increasing, decreasing, increasing, decreasing. So let's start with the second derivative graph. So at -4, at 0, and at 4 are intercepts. That's when the second derivative is equal to 0. Those are our points of inflection. So at -4, let's make this a little bigger. So here at -4 and at +4 and at 0 are when the second derivative is equal to 0. Those are my intercepts for the second derivative graph. And then this just tells me above and below. So before -4, it's above, and then it's below, and then it's above, and then it's below, and it stays below. So above, below, above, below, and there's a sketch of the second derivative. This one I need to make sure I count to 6 at least. But 4 and -4 is going to matter too, and 0. So now this is a graph of the function itself. And the graph of the function, we're going to follow the number lines. So what's happening at -6? We have a minimum. So I'm going to put a minimum kind of below -6. I can anchor that anywhere because they didn't tell me where that is. I just make sure that that's a minimum. And so we're starting the graph concave up and decreasing. At -6 it turns. And then what happens at -4? Well, we're going to do a point right there. At -4 it no longer is concave up, it's now concave down, but it continues to increase all the way to 0. So concave down, concave up, concave down to 0. At 0, it continues to increase, but the concavity changes. I just need to put a point above that. So it goes concave up, concave down, concave up. And then what happens at 4 is it changes concavity again. I need another point at 6. That's above. From 4 to 6, it's concave down, and then it decreases all the way. And then when I'm done, I look to see what I did. So, what did I start? Start with this first. First derivative. Does it decrease to -6? And then does it increase all the way to +6 and then decrease? So is decreasing and increasing match? The next part, concavity. Is it concave up to -4? Is it concave down to 0? Concave up to 4? And then concave down throughout? Are my turning points in the correct spot? And there's a picture that matches the first and second derivative. I didn't say it was easy, but as we practice this, to be able to interpret derivative graphs is big right now in calculus. That is a big concept one. That's big on the AP exam, that you have practiced and understand the concepts of what derivative graphs can give you for the main function. All right, number 11. Oh, we got one more. You're going to have to learn to love the graphs and love interpreting it and love the challenge of interpreting it. So again, this is a derivative graph. And so let's see what information I can get from it. So first of all, the first thing I'm looking here is where is the x-intercept? And the x-intercept's at 0, and it's above to the left and to the right. This graph will increase everywhere. It never decreases, and there's no turning point. For the second derivative, no at 0 is a turning point, but really more importantly, the derivative is undefined because of the corner or the cusp. So this is going to create a asymptote or maybe a hole, and decreases and then increases. So let's graph this to get a sense of what this would look like. So the second derivative, what would the second derivative look like? So at 0, if this was an asymptote, what I do know is that it's below and above. And the reason I do this curved is because this is curved. Notice the concavity, right? That it's concave down. That concavity also affects that it's decreasing and so on. This is also concave down. So both sides are decreasing. So it is below and above, and it's decreasing on both sides because both sides are concave down. It's a challenging one to interpret. The next one, at 0, and I'm just going to put that right in the middle of my graph, I know it's increasing on both sides of it, but the concavity changes. So this is concave down and then concave up. So concave down, concave up, and it's increasing throughout. It's important that what I'm doing here is matching the graphs that I see. All right, you probably have had enough of graphs. I think we're moving on here. Number 12. Well, we're not, but a different type of graphing. So number 12 says, find the asymptotes, behavior extreme, and then graph it. So let's look at number 12 to see if we can do that. So in number 12, I'm going to factor the denominator. Let's make sure that I don't run out of power. I'm just noticing that right now. Plug that in. There you go. Perfect. All right. Hey, here's my daughter. That's Juliana. So the first thing I look at in number 12 is I want to find where the asymptotes are, so I have to factor the denominator. So if I factor the denominator, two numbers that multiply to -8 and add to -2 would be -4 and +2. So I'm going to do that first. So let me show you my work in terms of what I'm doing. Move my paper up here. So at -4 and at +2. So I know there's nothing to simplify here. So the zeros of these, so +4 and -2, are vertical asymptotes. I also want to be able to, and there's no x-intercepts here at all. I want to take the derivative of this. So how do I take the derivative of this? Oh, I want to do the end behavior too while I'm here. So do you notice the bottom is more powerful than the top? So the power term on the bottom is x squared and just 1 on top. So that means the end behavior on both sides is 0. If I wrote that as a limit, that's what it would equal. So on both sides, positive and negative infinity, it's going to 0. And doing that. Okay. We got some drama here. So I need to take the derivative in order to find where it's increasing or decreasing. So let's do that right now. So when I take the derivative, I'm not going to do the factored form. So the other form I'm going to put here, that's x squared minus 2x subtract 8. I have to use the quotient rule. So the quotient rule is the bottom times the derivative of the top. So that's good because that's just 0, minus the top times the derivative of the bottom, which is 2x minus 2, and then take the bottom and square it. So I'm going to simplify it. I'm really just going to need to look at the numerator. So 0 times this is gone. This is going to be negative 2x, and a negative times a negative is positive 2. So again, the denominator is not going to affect much here. So if I want to solve, like make it equal and solve, all I need is the numerator, thankfully. So I'm going to add 2x and divide. So at x equals 1, the first derivative is equal to 0. So I'm going to do that. Then when I look here, what I'm looking for is if I plug in a number smaller than 1 or bigger than 1, is the answer positive or negative? Is it increasing or decreasing? So the denominator will always be positive because it's being squared. It's the numerator. So if I plug in 0 or a negative number, it's going to be a positive over a positive. So this is increasing. I also need to be aware of the asymptotes as well to make sure Positive 1 is not asymptote, so it's okay. So next, when I look at it, plug in a number that is bigger than positive 1, you know, like 3 or 4, and notice it's going to be a negative over a positive, which is negative. So at 1, what we just found is a maximum for this graph. So I'm going to plug that number 1 back into here to figure out what's the y coordinate that goes with it. So that's negative 3 times 3, so that's negative 1/9 if I like plug it back in, I believe, right? So at negative 1/9 is a maximum. There is no minimum. So it just has one turning point, and that's at 1. Next thing I'm going to find, did it ask for concavity? No, I don't know. Did it ask for concavity? Relative extreme points, if there's any points of inflection. Oh, and it gives you the, no, I'm looking at the wrong one. 12. End behavior is relative extreme. It does not ask for concavity here. So I'm just going to finish the graph off then. So for this one to finish the graph off, I'm going to focus in on the vertical asymptotes, which are at 4 and at negative 2. We have a horizontal one at 0. At 1 and negative 1/9, so that's just a little below, we have a relative maximum right there. It's just a little bit below. And now I'm just going to continue my graph in terms of what I know. So for a vertical asymptote, it's either going to be up forever or down forever. So this is the only point I know. So I know on this side it's going to go down forever. I also know if I plug in 0, I get negative 1/8. It's going to cross here in terms of this. This is what the picture is going to look like in the middle, because there are no x-intercepts. And so on both, it has to go down forever, which means on the other side, it's going to go up forever. And then the end behavior goes to 0. And again, on the other side, it's going to go up forever, curve with the end behavior being 0. So, again, I want to tell you that when you look at the factored form, because it has an odd exponent, it means that these are odd vertical asymptotes. That means on one side it goes up forever, and on the other side it goes down. They go in opposite directions. All right, number 13. Let me just pause this and I'll come back to number 13. And I'll be back.